We're pleased to have Alex Rasmussen from Stanford, who'll be talking about disintegrating the curve graph.
Okay, thank you very much for the invitation. This is all joint work with Mladen Besfina and Ken Bromberg. And I also want to give special shout out to Ursula Hamenstadt. So the main theorem we'll be stating today was stated by Hamenstadt quite a few years ago. She never ended up writing up a proof, so we give the first proof. But certainly we owe a big debt of gratitude to Hamenstadt. Okay, so our goal is to gain a little bit more control on the geometry of curve graphs. And we're going to do this essentially by taking them apart into simpler spaces, namely quasi-trees. And this will yield a new proof of finite asymptotic dimension for curve graphs. So first, let me just say what asymptotic dimension is. So this is some kind of large scale notion dimension for metric spaces. We say X has asymptotic dimension to most n. If for all r greater than 0, there's a cover of X by bounded diameter sets called U, such that every r ball in X intersects at most n plus 1 sets of U. Okay, so that's what it means for the asymptotic dimension to be at most n. And the asymptotic dimension is just the infimum of the n that work, or infinity if there's no n that works. Okay, so as an example, the asymptotic dimension, the Euclidean plane, is what you would expect to. So let's try to show at least that the asymptotic dimension is at most 2. So going back to the definition, we need to choose some cover by bounded diameter sets such that every r ball intersects in most 3 sets. And the cover we're going to choose is a cover of the plane by squares where they're large compared to r. So this is how the squares are going to be arranged. So they're arranged into layers, and when you move from one layer to the next, the squares are offset by like half a square. So why is this a good cover for this definition? So you want to see how an r ball intersects the different squares. There are 3 things that could happen. So these are 2 possible r balls. The worst thing that could happen is if your r ball is centered somewhere near a vertex, in which case the ball intersects 3 squares. And that's the absolute worst thing that can happen. So that shows you the asymptotic dimension is at most 2. In fact, it's equal to 2, but that requires more work. One other fundamental example that we want to keep in mind through the rest of the talk is the asymptotic dimension of a tree. Again, it's what you would expect, just 1. So let's keep that in the background. So why should we care about asymptotic dimension? Well, the first main reason to care is it gives us a group invariant. So it's invariant under coarse isometries. This is weaker than quasi-isometry. In particular, this gives you a well-defined asymptotic dimension for a finitely generated group. The other main reason to care is the Novikov conjecture. So I can't really do this conjecture justice, but it's a very important open conjecture about high-dimensional manifolds and cohomology. It turns out that for a group, if it has finite classifying space and finite asymptotic dimension, then it satisfies the Novikov conjecture. So that's a pretty cool connection from this metric space notion to some high dimensional topology. Okay, so we need to talk about surfaces now and mapping class groups and curve graphs. So I'm going to take S to be a closed oriented surface of genus at least 2. We could allow the surface to have punctures throughout the talk, but that'll just make statements slightly more annoying. So I'm just going to take the surface to be closed. And then we have some objects associated to the surface. We have the mapping class group. This is the group of orientation preserving homeomorphisms up to isotopy. And then we have the curve graph. So the vertices of the curve graph are the isotopy classes of essential simple closed curves on S. And there's an edge between isotopy classes alpha and beta if they have disjoint representatives. Okay, so what am I talking about here? First of all, this is a picture of some curves that are not in the curve graph. So the blue curve is not simple. Green curve is inessential. It bounds a disk. So these are not curves not representing the vertices of the curve graph. Here are 3 curves that do represent vertices of the curve graph. And how are they joined up in the curve graph? Well, blue and red are both joined to green by edges, but blue and red cannot be made disjoint, so they are not joined by an edge. So we get this little tiny subgraph of the curve graph, like so. Okay, so again, we have this correspondence between these curves and this little subgraph of the curve graph. Okay, a geodesic metric space X is delta hyperbolic for all triples X, Y, and Z in X. Any geodesic from X to Z is contained in the delta neighborhood of any geodesic from X to Y, union with any geodesic from Y to Z. Here's the standard picture for that. So X, Y, and Z will be the vertices of a geodesic triangle in X. And what we're saying is that if you take any one side of this triangle, it is contained in the delta neighborhood of the other 2 sides. So this captures the property of triangles in your space curving in on themselves. Examples of hyperbolic metric spaces would be trees and n-dimensional hyperbolic space. But the fundamental theorem for this talk is Maser-Minsky's theorem that the curve graph is a hyperbolic metric space. Okay, so we'll just keep that in the background as well. Okay, so what is known about asymptotic dimension so far and how it pertains to surfaces? So if G is a hyperbolic group, then its asymptotic dimension is finite. That was proven by Gromov. Nolan Fujiwara showed that the asymptotic dimension of the curve graph is finite, but they didn't give any effective upper bound on the asymptotic dimension. They just showed that it's finite. Vespina, Bromberg, and Fujiwara used this to prove that the asymptotic dimension of the mapping class group is finite. And more recently, Vespina and Bromberg gave the first effective upper bound on the asymptotic dimension of curve graph, showing that it's at most 4G minus 4, and this also gives you an upper bound on the asymptotic dimension of the mapping class group. So this leaves plenty of questions. We have some upper bounds. What are the asymptotic dimensions of these objects? The current best guess is maybe the asymptotic dimension of the mapping class group is equal to its virtual cohomological dimension. In fact, it's not known whether there's a group for which asymptotic dimension and VCD are both finite and not equal. So knowing the asymptotic dimension of the mapping class group would be very interesting, whether it's equal to VCD or not. So we're definitely not going to answer these questions today, but they're good questions to think about in general. Okay, so here's our main theorem. Again, this was first stated by Ursula Hammenstadt and proved by Vesvina, Bromberg, and me. So this is taking the curve graph apart into quasi-trees. So we have our closed surface, then there's a sequence of graphs, CK, with maps from one down to the next, such that each CK is hyperbolic. The graph at the top of the sequence is quasi-isometric to the curve graph. All of these maps are distance non-increasing. The graph at the bottom of the sequence is a quasi-tree, meaning just quasi-isometric to a tree. And lastly, for any bounded set inside of one of these graphs, CK, its pre-image and CK plus 1 is contained in a quasi-tree. So the last point is probably the most mysterious. So we really want to think of this theorem as building the curve graph up out of quasi-trees. So we kind of think of the graph at the top of the sequence as the curve graph. And then we can start at the bottom of the sequence at C0. C0 is a quasi-tree. And how do we get C1 out of this? Well, there's a map from C1 down to C0. Okay, and we can think about the fibers of this map. So the last point in this theorem is roughly saying that the fibers are quasi-trees. So if you take a bounded set, not necessarily just a point, its pre-image is contained in a quasi-tree. So this is saying something like C1 fibers over C0 with fibers that are quasi-trees. So we get one graph out of the next by adding on quasi-trees, basically. So what does this have to do with asymptotic dimension? Well, remember, trees have asymptotic dimension 1. Quasi-trees also have asymptotic dimension 1 because asymptotic dimension is invariant under quasi-isometry. So how does the asymptotic dimension change as you move up this sequence from C0? Well, at each step, the asymptotic dimension can only increase in the way you expect, so it can only increase by at most 1. So we get as a corollary for each k, the asymptotic dimension of ck is at most k plus 1. In particular, the asymptotic dimension of the curve graph itself is at most 4g minus 4, which is the same bound that Vesvina and Bromberg got using different methods. Okay, so this is all stuff that was known in some sense previously. Here's a theorem, which is all new stuff. So first of all, there's an explicit description of the Gromov boundary of any one of these graphs. There's an explicit description of the loxodromics and the action on any one of these graphs. And any other mapping class which is not loxodromic is elliptic. And the action on CK is acylindrical. All right, so this is so far just a really vague statement of a theorem. I'll try to make the statement more concrete later on. First of all, what does this last point mean, acylindrical? So the action of G on X is acylindrical if for all epsilon greater than 0, there exists R and N greater than 0, such that if the distance between X and Y is at least R, then the number of group elements G moving x and y, both the distance of most epsilon is at most n. So this is a weaker form of proper discontinuity. So in proper discontinuity, we would have for any point, there's a bounded number of elements moving that point at most epsilon. Here we can't say that, but at least if we have two very far away points, there are a few group elements moving them both a small distance epsilon. But yeah, bounded distance at least. Okay. So acylindricity is something that geometric group theorists care a lot about. It implies a lot of really nice things about the action. In particular, there's a lower bound on asymptotic translation length on CK. Asymptotic translation length is defined like this. You take a group element G, raise it to some large power n, apply it to some point x, which you fix beforehand, divide by n, and take a limit. So the asymptotic translation length quantifies how far G translates along an axis roughly, if it has an axis or a quasi-axis. And if it doesn't have a quasi-axis, then its asymptotic translation length will be 0. So what we're saying here is that there is some fixed number ek greater than 0, such that whenever a mapping class G is loxodromic, its asymptotic translation length is at least ek. Okay, so I want to now try to tell you what these graphs actually are and maybe state that theorem we stated a second ago in more concrete terms. So to do this, we need to talk about train tracks. A train track tau on S is basically an embedded graph with edges tangent at the vertices. So there are more conditions than just this, but I don't want to get into the technicalities. So here's a picture of a train track. So it's some kind of embedded graph. And as you can see, the edges are tangent at every vertex. A measured lamination carried by tau is a function W from the edges to the non-negative real numbers, satisfying the switch equations. Switch equations just say that at a vertex, the sum of the weights of the incoming edges is equal to the sum of the weights of the outgoing edges. So this gives us a set W of tau, which is the set of measured laminations carried by tau. Okay, so a measured lamination is a function from the edges to non-negative real numbers. So this is naturally a subset of R plus to the power of E of tau. In fact, it's a polyhedral cone, but we don't really need to dwell on that fact too much. And this sits inside of a larger space, ML of S. This is the set of all measured laminations on S. So here we're explicitly not fixing a train track beforehand. We allow the track to vary. We allow the lamination to vary, and we get some kind of big space. And this is all to define the index of tau, which is the codimension of W of tau and ML of S. So basically, we want to just think of this index as some measure of how big tau is. So if you have a larger train track tau, then you get a smaller index. Okay, and the index is the thing that we crucially use to define these graphs. So what are the graphs CK? Well, the vertices are the same as the vertices of the curve graph, just all essential simple closed curves up to isotopy. And we join alpha and beta by an edge if they're both carried by the same track tau, which has index greater than k. carried here, you can just imagine to mean smoothly immersed in tau. Okay, so this definition is probably kind of opaque right now. So I want to say a couple things to give a little bit of intuition on what this edge relation is about. So first of all, there are more edges in CK than there are in the curve graph. So not only are curves joined by an edge when they're disjoint, but also when um, they fill the surface, chop it up into polygons, and the polygons have some large numbers of sides. So essentially, you're making things closer together in CK, and the only things that can be far apart are pairs of curves that cut up the surface into really small polygons. To say something about this intuition, there's some way to construct train tracks out of pairs of curves by smoothing intersections. Here's a picture. So we have two curves. One is the kind of dashed curve, and the other is the solid curve. And we can turn this into a train track by saying at every point of intersection, I want the dotted curve to turn left. If we do that, we get a train track that looks like this. And notice that polygons in the complement of these two curves correspond to polygons in the complement of the resulting train track. Okay, so roughly, very roughly, and I'm kind of lying here, alpha and beta are joined by an edge. This approximately means that the train track we constructed is small, index greater than k. Of course, this is not the actual definition because tau in the definition can be any track carrying both alpha and beta, but we'll ignore that for the time being. So what does it mean if tau is small, index greater than k? So let's think about the converse. What if tau is large? If tau is large, then it cuts the surface up into really small ideal polygons with few sides. And well, there's this correspondence between the polygons in the complement of tau of alpha beta and polygons in the complement of alpha union beta. So roughly tau of alpha beta is large if alpha and beta cut S up into polygons with few sides. So kind of the only way to not be joined by an edge in CK is if alpha and beta cut up the surface into polygons with few sides. Again, that's just kind of the rough intuition. As an example, alpha and beta are not joined by an edge in C0. The only way for them not to be joined by an edge is if any train track carrying both of them is maximal, and this in turn is equivalent to the complement only containing quadrilaterals and hexagons. So those are the smallest polygons that can live in the complement. Okay, so now we can state our theorem for real. The boundary of CK is the space of minimal filling laminations, lambda on S, such that any train track tau carrying lambda has index less than or equal to k. So these are large minimal laminations where large is quantified by k in some sense. Minimal means every leaf is dense. Filling means the lamination intersects every essential simple closed curve. And a mapping class phi will be loxodromic on this graph exactly if it is pseudo-Anosov with fixed laminations lying in this boundary. So as an example, the boundary of C0 is the space of maximal minimal laminations. kind of sounds like an oxymoron. It's really not. This means every leaf is dense, and the complement of the lamination is a union of ideal triangles. And finally, just to bring things back down to earth for a moment, let's give some examples of mapping classes that do or do not act loxodromically on this graph. So in this picture, we have three multicurves, alpha, beta, and gamma. So you can construct pseudo-Nosovs out of these using Penner's construction. We do the left Dane twist on alpha composed with the right Dane twist on beta union gamma. Then we get a pseudo-Nosov, which is loxodromic on C0. But if we leave gamma out, we again get a pseudo-Nosov by Penner's construction, but this time it does not act loxodromically on C0. And the difference has to do with the polygons that exist in the complement of these three multicurves. All right, so that's going to be it. Thank you very much.
Okay, let's thank Alex. And if does anyone have any questions? You can ask in the chat or come off mute. I have one. Like, is there possible to like just the first bit where you have this like map between hyperbolic spaces and you have fibers being quasi-trees? Is that known for like a more general class of groups? Like, I don't know, maybe right angled Darton groups or other HHGs?
Yeah, okay, so I think, okay, so a very important part of this theorem is that these graphs and maps are all equivariant. Yeah, so these maps Fi are equivariant. Now, I think it's actually known that if you have a general Gromov hyperbolic space, then it quasi-isometrically embeds in a product of trees. I believe that's true. But doing this equivariantly is much harder.
Okay.
Yeah.
Any other questions?
Just a quick question. Like here, all the FIs are just like the identity on vertices, or
That's
is it-
right.
Okay. Thank you.
If there are no other questions, let's thank Alex again.